Okay, so in the last part we have proved these things, that for every natural number n there exists a unique pair of subsets of n, an and bn, which satisfies these properties. And then we say that one can proceed to prove, next using these things one can proceed to prove that for every natural number n there exists a unique function an from this set an into the set of natural numbers that satisfies these conditions. And we mentioned that the proof is exactly similar to the one we did when in place of an we had this set. The set of all natural numbers less than or equal to n. But we also mentioned that there are some, although the proofs are similar, but there are some differences. So those differences we will just quickly point out. Actually the solution is over, we just want to say some extra things. So let me just write how we were writing in the previous video. This can be proved by induction on n in a manner similar to the first paragraph. And now within brackets we write that extra thing. Despite this similarity, there are some differences. Although the arguments are similar, their justifications may be slightly different. To see what that means, we go through a part of the first paragraph. In this new setup. Okay, so in the first paragraph we were also proving a similar statement, but there in place of this we had the condition that n is a natural number less than or equal to n, actually strictly less than n. So that has been replaced by this here. Okay, so and that we were doing by induction. So suppose we have the induction hypothesis. And the hypothesis now looks like, actually it's just that let us just once more write it. For some natural number in there exists a unique function an from an into n such that an of 0 is c and the value of an at the successor of small n equals f of n comma the value of an at n. For all n in an that are not equal to capital N. So basically this is just what we are stating here. The only difference is that this is a statement that we are claiming it to be true for every natural number capital N, and here we have assumed that the statement is true for some natural number n, which is not nothing fixed, it's arbitrary, but now we have to prove it for the successor of capital N, n plus plus. So just like the first paragraph of this solution, we define a new function an plus plus. Now define from this set into the set of natural numbers by the following formula. So its value at the natural number n is defined to be equal to the value of the function an at n if n belongs to an, right, and is defined to be equal to this if n is equal to n plus plus. Keep in mind that according to our according to the way we constructed these sets, this an and bn is also there, which is nothing but the complement of an in the set of natural numbers. So according to that construction, if you go to the previous video, you will see that an plus plus is nothing but an union n plus plus. That's how we went forward, and this is the only possibility because not only do these sets exist but they are unique also. So that's why whenever you have n in the domain an plus plus, either that n is in an or it is equal to n plus plus. Okay, oh sorry, I wrote this will be capital N. Sorry about that. Okay, so either this will be let me just write capital N here also, then it will be clearer. So either the variable will be in the set an or will be in this set, which means it will be equal to capital N plus plus. So in both the cases we have definitions. So that's how we define an plus plus, which is not much different from what we did in the first paragraph. The only difference is that in place of these steps you have some other step that looks like, in place of, for example, this one, you will have this. That is the difference. But since in the second half we are not allowed to use order or any other such structures, so we are adopting this new approach. Okay, now for an plus plus we want to show those things, these properties. We have an plus plus at 0 is equal to an at 0, which is equal to C. But how? You see, 0 must belong to an for this calculation to make sense, because then only I can use an of 0. Now does 0 belong to an? Yes, it belongs to an, because by condition C, 0 belongs to an. Those the properties that these sets an and bn satisfy, though they are always there in the background, and we have to use them because we don't know anything else about these sets. Only those properties are there. Okay, so this part is, there is no problem with this. Now let n belong to, next we want to say see whether this property is true when you have n plus plus in place of n. So here you would choose n belonging to an plus plus minus n plus plus. Okay, so then n belongs to an plus plus, which we already know is equal to an union n plus plus, but at the same time n is not equal to this, so n has to be in an. Let us see what we get from that. Comma, we can write like this, which implies n must belong to an. Okay, if n plus plus belongs to an, then n plus plus, the successor of n, may or may not belong to an. If it belongs to an, then an plus plus n plus plus. Since this n plus plus belongs to an, so we can use this part of the formula and write an of n plus plus. Okay, and now can we use the formula that we already have? in our induction hypothesis, this formula. This we can use if small n is in an, which is true, but small n is not equal to n. Okay, so let us see, there will be cases. So this is equal to, say we write like this, f of n comma an of n, okay, which itself is equal to f of n comma an plus plus of n. How can we write this to be equal to this? That we can do, because n anyway belongs to an. So when n belongs to an, this and this are actually equal. So in place of this we can write this, provided, we should not forget the condition which is making all these things happen, provided n is not equal to n, because then only we can use this condition which we have used there. Okay. If n is not equal to n. Now the question is, can n be equal to n? If n is equal to n, then n plus plus is equal to n plus plus, naturally, because they are the same thing, and hence you see we have here n plus plus belongs to an. So in this case, n plus plus, capital N plus plus will belong to an but by condition. What was that condition? That was condition D. Condition D, n plus plus belongs to Bn, and by condition A, an and bn are disjoint. So this element now is contradicting the disjointness of an and bn, because it belongs to both an and bn. This contradiction shows that if n plus plus belongs to an, as we have assumed here, then n is not equal to n. Then we cannot have n equal to n. So this provision that we need here for this formula to make to make it work, that is already true. We don't need to assume it as an extra condition. So this is true when n plus plus belongs to an. Okay, now but there is one more condition. If n plus plus does not belong to an, what then happens? If n plus plus does not belong to an, then by condition D, E, F, then by condition F, we must have okay, by the way, what does condition F say? Condition F says that if something is in AN and that thing is not equal to capital N, then this implies N plus plus also belongs to capital N. Now if this condition is not true, what we have here, then either this is false or this is false, the contrapositive. So let us see what we have here. We already have N belonging to AN, so this condition is already there, so we cannot have we cannot have this, so N has to be equal to capital N. Then by condition F we must have, I hope you get this part. Here we have used the contrapositive because we already have this thing, so that means that the negation of this would imply the negation of this, which itself is a conjunction, something and something else, so its negation will be a disjunction, negation of this or negation of this. Now this is already true, so the negation of this must be true. Okay, so this is already true means its negation is false, so negation of this must be true. Negation of this means N is equal to capital N. So we must have N equal to capital N. Okay. Now if N becomes capital N, then what happens? In this case, AN N plus plus, this is the other case, keep that in mind. One is this when N plus plus belongs to N, and the other is this when N plus plus does not belong to AN, sorry. So I should write N plus plus here. This is equal to AN plus plus N plus plus. Now you just use the formula that is given here. When small n is that is when in place of small n you have capital N plus plus, then this is the formula. So we can use that and write, let us see, let's not rub this off immediately. Then this is equal to f of N AN N. Now since capital N itself belongs to AN, so in place of A capital N we can write A capital N plus plus. Okay. Now you can, if you want, you can replace capital N by small n, because that's what it is right now. In brackets you write since by condition G. See, I have included condition G in their original given list in the hint, because we need this here. You see, by condition G, n belongs to an, and that's why n also belongs to an plus plus. It belongs to an as well as it belongs to an plus plus. So that's why, since the functions are the same in the set an, so that's why you can replace a capital N by a capital N plus plus. They have the same effect on capital N. So now you see what we have achieved. We have proved, where is it? We have proved this property for any n, whether that n is like this or like this or like this. In any case, the formula is true. You see, an plus plus n plus plus is equal to f of n an plus plus n. Here also an plus plus n plus plus is ultimately equal to f of n an plus plus n. So that's how we can achieve all the things. And actually this is, we are doing nothing new. This we have already done in the first paragraph. Only the arguments and arguments were also same, but the justifications were somewhat different. Here you see, we are again and again using the conditions that way. That's how you see how the conditions are actually needed for those sets. And recall that we started this off with a bracket. The rest means then you will show that these functions are actually unique, then use them to construct that function, remember, which satisfies so and so properties. Actually existence of this function and its uniqueness is the ultimate goal of this solution or of this exercise. So that can be done. The rest is, of course, just like the first paragraph. I decided to include this part just to show how the conditions will be used. Now comes, here actually the solution ends, but I want to include an observation about this solution, without which you cannot proceed any further in whatever we are doing. You see, what does proposition 2116 tell us? It tells us that if we have a function from n cross n into n, which okay, if we have such a function and we also have a natural number c, then there exists a unique function which satisfies so and so properties. You already know what properties A satisfies. Okay, what do we get from this? Look at this function A. It actually is a sequence of natural numbers, because it's a function from the set of natural numbers into the set of natural numbers. So this second set is the set where the functional values will appear. They will appear from the second set. Like the first functional value is C, then the next functional value is this f of 0 plus plus, a of 0 plus plus. by our formula, this is f of 0, a of 0, which is nothing but, and ultimately this is again a natural number. So the terms that we get in this sequence, they are all natural numbers. So we end up having a sequence of elements in the second set. Now you can see, if you look carefully in this whole proof, that in place of this second set, you can, I mean here in place of this set of natural numbers, you can have any set actually, any non-empty set, and the same proof will work. So that observation I want to make, because if you use only proposition 2116 in the form that it is given, then you will be able to generate only sequences of natural number, or the principle of recursive definition can be applied to generate only sequences of natural numbers, but we need sequences of other objects also. For example, sequences of real numbers we will need, sequences of vectors or matrices, those things we need. So we need a generalization of the principle of recursive definition. That's what I am going to write right now, and the proof is exactly same. So don't worry, we don't need to again go through a long proof. Okay, I would like to write the observation like this. Okay, let me just refill a bit. And the observation that we will write here now will be used in the very next exercise, which is the last exercise, the 13th number. The above solution makes us make the following observation. A general form of proposition to 116 is also true where, or using which we can generate sequences in an arbitrary non-empty set. More specifically, if A is a non-empty set, A is okay. To emphasize the fact that A can be any non-empty set, let us just write any. And C be any element in A. So now C is not a natural number. C is any element in the arbitrary set A. Also, let f from n cross A into A be a function. Then there exists a unique function A from n into A such that A of 0 is equal to C and A of n plus plus is equal to, statement is same, meanings are somewhat slightly different. For all natural numbers such that n is less than n. Okay, so here the difference between this one and the previous one, the actual statement of proposition 2116 is that here we have a general set A. Note one more thing, that we are again using order. There is